So our next speaker is Taihao Han from Missouri University of Science and Technology.
Hi everyone, I'm Taihao Han from Missouri ST. Today I'm going to present design and discovery of sustainable cementitious benders through machine learning trained from a small database. So as we know, concrete is a major material for infrastructures, for constructions. Due to the population increase, we can expect another additional 20 billion tons demanding of concrete from now to 2050s. The cement is a major component of concrete. During the manufacture of cement, it releases a lot of carbon dioxide. So this contributes to the decarbonation of the limestone and burning fossil fuel to calcination the raw materials. So nowadays, people want to reduce carbon dioxide emission to produce sustainable cement. So what can we do? Some researchers may say, okay, we can try the carbon dioxide capture system, but due to the high cost, only few cement plants they are willing to upgrade their infrastructures. And some researchers also said, okay, we can try some clean energies to calcinate the cement, but nowadays still 70% of electricity is generated by the burning coal or fossil fuel, so it just transports the carbon dioxide from one place to another place. So nowadays, I think the most practical way to use supplementary cementitious materials to partially replace cement that can significantly reduce the cement use. So the replacement level can reach to 50%. So that means you don't need to use half of the cement in your construction. So that can help to reduce carbon dioxide emission. So for the SCM, it has nature minerals like limestone cores. Also, we can use industrial waste, something like the fly ash, waste glass. But due to the different compositions, you can expect each SCMs can affect the property of cement in different ways. Here is some examples. You can see this one type of fly ash. You increase the replacement levels. You can see it changes the hydration kinetics of your cement. And here another type of fly ash. So it has totally different influence on the cement hydration kinetics compared to the previous one. So here's the third example. So you can see some fly ash can increase compressive strength, some may decrease compressive strength. So in our study, we want to focus on the influence of SCMs on the hydration kinetics of cement, because we think this properties is one of the most important properties for cement. So because if we know the heat release from the cement during the hydration reactions, we can use that to know the degree of reactions, and we can combine with the thermodynamic simulations, know your microstructure of your cement. We also can use the heat release to estimate other properties, for example, compressive strength, the workability of your cement. Usually people investigate property of cement. They do experiments. They take very long time to do experiments, but this is not cost efficient, also not time efficient. So in our study, we want to develop some models that you just click button, and then it gives you the property of your cement, of your sustainable cement benders. So you don't need to do experiment, so save money, save time. So the first model we think we can try the traditional theory-based model, like nucleation and growth model. So in this model, it accounts for the cement SCMs, and you group the cement hydrates on the surface of those particles here. And this is the simulation results. You can see the nucleation and growth rate model produce excellent fit to the measured value here. However, to use this model, we need to know three very important parameters. We need to guess these three parameters. First, the effective surface area of SCM. Some SCM have fine particles, so you can expect agglomerations. In that case, you have less effective surface area to grow your hydrate. So, but this number is easy to guess. It can be guessed based on the researcher experience. And the second parameter is nucleation density. So that means how many nuclei can grow on the per unit areas. So some study has measured that value. So we know that values. We don't. They give it a range. So in that range we can guess a number. But the third parameter is the most important one. So the growth rate of your hydrate. So that is a time-dependent variables, and you cannot use experiment to measure it. I know some study trying to measure it, but the results are inaccurate. So also the model is sensitive to that parameters. If you small change in that parameter, you can totally reverse your hydration behavior of cement. So researcher cannot guess these parameters. So that means this model can be only applied to a system you know you have those parameters. But if you give this model a new system, the model cannot predict the hydration behavior for your cement. So what can we do? So we try another model, machine learning. So machine learning is artificial intelligence. So first, the researcher need to do some experiment to get some results, and then you use the experiment data to train your model. So the model can learn input-output correlations by itself. It also can automatically adjust internal parameter. You don't need to do the manually adjust. That can reduce the human errors. Also, when after the machine learning model learns your data, you give your model some new system. The model can predict the property for you. So in our study, we have a small database, contains hundreds of data records, but it's highly diverse. So we have, in that database, we have commercial and synthetic cement. We have more than 10 SCM, basically includes all the common SCMs here. So the input and output is the input is a physicochemical property of your SCM and your cement. The output is the heat flow rate of your during the hydration reaction. Here is the prediction results. So you can see it can do a good predictions. So you do not need free parameters. You just need to simple input variables. You can produce a good predictions. But still, you can see the model is hard to capture the trend at the peak. Also the trend for those ternary systems. So this is because the input-output correlations at the hydration peak, also for the ternary system, they are complex. So we don't have enough data to train the model. So the model cannot sufficiently to learn those complex input-output correlations. So what can we do? So most studies to recommend use a larger database, very large, content of thousands, even millions of data record, but it's not practical for us. So for cement, if you want to collect one data point, like 28 days compressive strength, you actually need to wait 28 days. So it's really hard to collect like thousands of data record. What can we do? So, okay, we want to try to simplify our database. So that makes the input-output correlation is much simpler. So the machine learning model can learn such simple correlations in that small database. So here I'm going to introduce three methods to reduce the complexity of the database. So the first method is segmentation. That method is the most simple one. So basically you divide the hydration profile into different segments, and each segment has a similar but simple trend, so that the machine learning model can easily learn the simple local trend instead of complex global trend. So in our study, we basically divided in 3 segments. The first segment is the beginning of the hydration. The dissolution of cement is a control mechanism for that segment. The second segment is the hydration peak. So the hydration reaction reached to its maximum levels. And the third one is when the cement start to set. So the hydration reaction start to decrease. So here is the prediction result. I'm not sure if you guys can see the color, but so the red one is model with segmentation method. The blue one is standalone model. So you can see the segmentation method improve the prediction performance here. The next method is fast Fourier transform method. So that is a fast Fourier transform is a mathematical method. So convert a complex waveform to a simpler format. So that's the method usually to use to processing the sensor signals. Here you can, so for this method, we basically transfer the heat flow rate profile into a simple format here, and then to predict the profile for that simple format, and then transfer it back. So you can compare that simple. So the transformed heat flow profile has much simple structure than the original one. Also, I can tell you, except for the first 2 points, the rest of the transformed profiles are symmetric. So you only need to predict half of point. That significantly saves the computational resource. Here is the prediction results here. So still the red one is model with the Fourier transform. So you can see the Fourier transform helps the machine learning model to learn the input-output correlations here. But still, the fast Fourier transform method is a mathematical method. During the transformation, it may violate some material laws. We don't want that happens. We come up another method. So that is a machine learning informed nucleation and growth models, as we see before. So the nucleation and growth rate to use the nucleation and growth rate models, we need to know the growth rate of your hydrate, but we cannot guess. But we can use machine learning model to predict that profiles, to predict the growth rate of your hydrate. And you can see the profile for the growth rate hydrates is simple than the heat flow rate profiles. No inflection point here, so the machine learning model is easy to capture those simple trends. So first we use the machine learning model to predict growth rate, and then we implement the growth rate to the nucleation and growth rate models to produce the final output. So here is the output here. So here the blue line is the model with the nucleation and growth rate model. You can see it much better than the standalone models, also better than other 2 methods. I think that's because the nucleation and growth rate model regulates the final output, so that can avoid the violation of materials laws. So here's some other application for machine learning. So for the machine learning, we can rank the influence of each input variable to find which input variables they are important, they are not important. So we can use such information to develop some analytical model to help us to understand mechanism behind the materials. We also can predict other properties for different type of materials here. The third one, if we know that our target properties, we can use machine learning model to optimize the composition to achieve the target properties. Here is the conclusion. So as we know, machine learning is a powerful tool. It can do the prediction, optimizations, simplifications. Also, in our studies, we introduce 3 simplification methods so that allow machine learning model to produce good predictions, even you have very small database. So that can help us to widely use the machine learning models to other type of concrete applications. So yeah, and also we in the future we can do some improvement, like as we know so far, when we use a theory-based model and a machine learning model together, we use side by side. It basically you use a little bit of separations here, but we want to develop some highly integrated model, something like you can use some material laws to like regulate the calculation in each neuron of your artificial neural network, something like that. I think that's all I have. Please.
I'm Jadiya from the University of Texas at Austin. Great presentation. I just wanted to ask you regarding the SCMs. Have you looked into the nature of the SCMs themselves? For example, for fly ash type C and type F, and the pozzolanic or hydraulic nature of SCMs, and can we index them for like a generalization of SCMs in terms of like an index of the pozzolanic nature, or like a number for pozzolanic, or the content of Al2O3, and like a certain index that we can quantify and predict based on it?
Okay, yeah, thanks for your question. So in our studies, we have tried different type of flash. Like we basically use composition of flash as an input variable so that we can consider all the flash. Also, we also try to consider the chemical structure of flash. In that case, we use a parameter called number of constraints, so it can to evaluate if the flash have more amorphous structure or have more crystal structure, something like that. So we have that information in our model.
I see. Thank you.
Can I ask a question myself? Taihao, in the machine learning approach for predicting reaction rates, I apologize if I missed. What are the main input parameters into the model?
So the input parameters, so like the physical chemical properties of your cement and SCMs. For example, how much, like for cement, how much the C3S you have, C2S you have, something like that. Also the particle size. For similar to the SCM, I said before, so we can use chemical composition of your SCM. We can use for like flash. We may also consider the structure, chemical structure. So we use all those parameters as input variables.
Okay, very good. And if I may kind of do a follow-up, for SCMs, do you include any measure of reactivity?
So that's why the reason we include the chemical structures. So in general, for the flash, so you have more amorphous structures, it's more reactive. If you have more crystalline structure, it's less reactive.
But you extract that information from the bulk chemical composition of the
SCM. And do some calculations to get that value.
Okay. All right. So you don't directly input a measured reactivity, like the strength activity index or the R3.
We don't do that right now. Okay. But we can include in the future that. So those parameters all can be included in the machine learning.
Absolutely.
So, yeah.